Thank you so much, everybody, for joining us in person and online. It's my pleasure today to introduce Suman Raj, who is visiting us from the Indian Institute of Science in Bangalore in India. She's a PhD student there working on Edge to Cloud, on the Edge to Cloud Continuum. Her supervisor is Professor Yogesh Simhan, and we're very, very happy to have her here working with us this semester. So welcome, Suman.
Yes, good morning, everyone. So as Eva said, I'm Suman Raj, and I'll be having my talk on this topic. This is Scalable Planning Platform for Orchestration of Autonomous System across the Edge Cloud Continuum. So let's get started with these basics. Like we have unmanned aerial vehicles, and generally these are called as drones. So with recent advancement in these sensors and the onboard compute, we have these drones getting integrated with these edge devices, such as Jetson Nano. And this integration is actually a good candidate, which can be called as a mobile edge computing and sensing platform, or in general terms, like a flying computer. So these fleet of drones that are integrated with these edge accelerators, they are used for a wide variety of applications like urban safety or logistics delivery. And recently they are also being used for some social applications like ambulance drones or to, help visually challenged. But even if we are integrating these unmanned aerial vehicles for edge accelerators, they can also be used for some of the scientific workflows like for disaster management or wildfire monitoring. And apart from edge accelerators, now if we look at the system side of it, we also can leverage the entire edge to cloud continuum and use that with these unmanned aerial vehicles and leverage the collaborative computing part of it. So what we can leverage is that we can offload most of the heavier workloads to remote cloud where we have infinite resources, and they can help us in timely processing of data. And this can, in general, like as an overview, help us in distributed data collection and analysis. So one of the application that we have tried to explore is if this kind of system can help visually impaired for navigation. And even though we propose our solution for this, the solution can be generalized to any other scientific workflow in general. So here's the proposal. We have buddy drones to assist visually impaired people, whom we call as VIP. And some of the current solutions for navigation assistant, they use like traditional methods like white canes or guide dogs. And some of the AI-powered walking assist, smart canes, and all of that. But one limitation of these things is that they are kind of a physical burden on the people, and they curtail their autonomy and just leave them with a limited field of view to which the sensors are pointed. So what we propose is that can we have like a drone-based platform which has like a flexible viewpoint, and that can collaborate across the edge and cloud such that they help the visually impaired. And even though we propose this kind of system where every person has an edge device and the drones are connected to that edge device, over there the scheduler and all of those intelligent heuristics run, and they send the control back to the drone for like a smooth movement. And they can also offload some of the tasks to cloud as well. But even though this kind of system like edge to cloud and drones, they can be generalized to any other app platform ecosystem for drone-based applications. So some of the challenges in this collaborative computing is that we will have some compute heavy workloads. Like for any kind of application, we need multiple DNN models. It's not going to be just one, because even if we are looking at, let's say, wildfire monitoring, we need something like fire detection, we need human detection, then we need path planning and all of that, right? So we need to have these multiple DNN models, and they require accelerators. So we need to have a mix of onboard edge compute because they are resource constrained, and we need to have some kind of remote cloud as well. The other thing is that when we are doing this collaborative computing, there is a heterogeneity coming in, and that does not just come in terms of compute power, it also comes in like the monetary cost that we pay for it. So the edges are a little bit of, like a little less costly, but some of the cloud services that we use. And we have like a pay-as-you-go cloud services. And recently, many cloud service providers, they are providing this serverless cloud option. The other thing is we need to have all of these models stored, like loaded in the memory so that they can be invoked as and when any task needs to be done. The other thing is if we have some kind of deadline aware application, we do have a latency sensitive nature so that it does not impact our safety. So we will have two very important stuff, that is a deadline and a benefit. So deadline takes care of the temporal importance of any kind of task, and benefit takes care of any kind of associated value that is derived out of it. The other thing is, since we are having this as a mobile application, since the drone is moving and the edges are moving along with the person, we have some kind of a connectivity between the edge and the cloud, and that can fluctuate whenever the person walks. So there will be this network variability coming in. So finally, with all these constraints in mind and all these challenges in mind, how do we actually guarantee some kind of quality of service to the users? So we have to maintain a task completion count within the deadlines, and we have to ensure that the utility that we accrue is maximized. So here is the architecture. So let's say we have these buddy drones, or these can be any kind of drones per se. And this entire box is like the platform that's sitting on the edge device. So whenever the drone video segments are coming in, we try to create the video segments and we try to extract frames out of it. So one intelligent way of doing that is extracting the keyframes out of the entire video. And once we have the segments out, we kind of create tasks for it. So let's say we have, for any application, we have like 2 to 3 models active. Then for every frame that's coming in, we create 2 to 3 tasks for every model. And whatever is the characteristic of the model, that gets assigned to the tasks. So now once the tasks are in the task queue, this task scheduler does the intelligent work of pushing it either to the edge scheduler or to the cloud scheduler. And depending on certain real-time situations, it has the option of migrating some of the task which has been scheduled to the edge again to the cloud, or maybe pull some of the tasks which are on the cloud back to the edge. So we kind of do all these things just to maximize the utility. One other thing to note is that since these edge accelerators are like limited compute, we run only one process at a time, which means one DNN model is active at a time. But since cloud is like infinite resource, we have a thread pool that keeps executing on the cloud. So it's like in an asynchronous fashion. So in this platform, we are using Jetson Nano as the edge accelerators, which can be replaced by, let's say, Jetson Orin Nano or Jetson AGX Orin, those devices as well. And we have AWS Lambda as the cloud. Yeah, and once we get the results back from either the cloud or the edge, that goes in the results queue. And once we have the control commands generated, that goes back to the drone and the feedback loop continues. So some of the important parameters of the task that we have, so these are more of inferencing tasks. We are looking at more of the tasks which do require DNNs, like deep neural networks. So we would have a video segment ID. We have some DNN inferencing model, like what is the model on which it is going to be executed. But two most important things are this deadline duration and the utility. So utility is something which we get, which we define, and this is more like benefit minus the cost. So cost is like pro rata based, and the duration of expected, like this is the expected execution time that is there either on the edge or on the cloud. So we benchmark some of the models on the edge or the cloud, and based on those numbers, we kind of estimate the cost of running a particular model on a device. And these costs are like real numbers. We actually take the monetary cost and use like it like operational. If it's operational for 3 years, then how much is the cost for like per second, and so on. So one thing to note over here is that if our task executes before the deadline, we do give it a positive benefit. But if the task executes, but it misses the deadline, which means we come to know that the deadline has been missed after the task returns back with the output, then we do not assign any benefit to it, which means that it is accruing a negative utility. And finally, if the scheduler identifies that this task is going to miss the deadline after it's executed and drops it beforehand, so we just assign a 0 utility. So over here, our objective is that we need to maximize our total utility, and we need to maximize the number of tasks which have been completed within the deadline. And even though this is like a dual maximization problem, we try to individually maximize these two criteria rather than a combination of them. So for this, we propose this heuristic called as DEMS A. And so this is the nomenclature like, so D is like, it is a scheduler for the drones. And we use earliest deadline first priority for the tasks which are being scheduled on the edge. So edge scheduler is actually using this EDF. And we have a task migration logic that takes place from edge to cloud queue. So this migration logic actually avoids the starving of the lesser priority task in the edge queue. And we have a work stealing that goes from cloud back to the edge, such that we increase the edge resource utilization and in turn reduce the overall cost that we pay to the cloud. And finally, we have adaptive, it is adaptive to variability. So this helps us mitigate the network variability that has been caused by the VIP movement. So yeah, so let's get through one of these. So the first one is EDF. So it guarantees that the chances of missing any task deadlines are minimized, which means that it is going to maximize your on-time completion task. So over here, the tasks that have an earlier deadline, they get a higher priority. And for every task, we do a feasibility check. So first of all, in the entire queue, in the edge queue, we check that if at all the task is going to get scheduled, is it going to meet its deadline? Plus, it has to also take care of whatever tasks are there in the queue already, such that if at all it gets a higher priority because of its lesser deadline, we need to ensure that the rest of the task which is there in the queue, that does not miss its own deadline. So if the check fails, the task is redirected to the cloud queue. And the cloud scheduler is just based on FIFO because it's infinite, so we can just keep sending requests. And over there as well, we check if the task can meet its deadline on the cloud or not. And if at all the utility that is expected from the cloud is non-negative. So yeah, so the other heuristic that we introduced to the EDF part is this migration heuristic. So what it does is checks if the existing task behind a new task that is being inserted into the edge priority queue, do they miss their deadlines or not? And this is done based on a scoring function. So we have a scoring function that assigns utility of edge minus utility of cloud to the task that executes on the cloud within the deadline, and the cloud utility is greater than 0. And if the task executes on the cloud, but it misses its deadline, then it is assigned a score of utility of edge. So over here, we always try and prioritize the task which cannot go to the cloud and which will be executing on the edge itself. So let's take an example. Now over here, we have this timeline of the edge queue. So let's say this is the time t is equal to 0 right now. And the t is equal to 1 is like the expected execution time, and delta is the deadline of the tasks. So for every task, we have like, let's say, some expected execution and some tasks. Now, let's say a new task arrives for which the expected execution time is 4 units and the deadline is 6 units. So now we have to check the score of task 5 and the score of task 3, because if we insert this task 5 into the edge queue, the deadline of the task 3 is going to be missed. So now when we check the score of both, it seems that the score of 3 is less than score of 5. So in that case, what will happen is that the task 5 will be inserted into the queue because the score of that is higher, and task 3 will be going to the cloud. So yeah, so this is how the migration logic takes place. This is just one illustration out of that. The other thing is, now let's say when we are migrating and doing all of this, now let's say what if we are overestimating our execution time, because sometimes it may happen that the task completed in like 80 millisecond and we estimated that it might take 100 millisecond, and based on that it is like migrating a lot of tasks or maybe just dropping a few tasks and all of that. So we also monitor the edge queue like always, and we also monitor the edge resource utilization. So if we steal the task from the cloud queue back to the edge queue, it might result in a better utility. And the other thing is the tasks which are sent to the cloud queue, sometimes they may be marked as a they may be marked as a negative utility task. So even though they are waiting in the cloud queue, just at the point of trigger, they might be just dropped off, because definitely they cannot be scheduled on the cloud because they have like a much higher cost of getting executed. So in that case, if we are stealing some of the tasks from the cloud queue back to the edge, this is like the opportunity where we might give these kind of tasks a chance. So yeah, so what we change from the earlier heuristics is we introduce one extra thing in the cloud queue, is that instead of just sending requests to the cloud as and when a request comes, we hold it until the trigger time, which means that deadline minus the expected execution time minus some buffer. So let's say if this is the state now, and if this is the initial state of the cloud queue and this is the edge queue. So over here, the edge queue is similar. It's just that the cloud queue has like 3 more tasks. And if we look at these features of the task which are there on the cloud queue, so we see that the utility on edge is always positive, but there are chances that utility on cloud is negative sometimes. So even though in this case, the task 5 and task 6, they both have equal possibility of coming back to the edge, because we have a slack of 1 unit, and this can be used by any one of the tasks in the edge. So out of both of these, we prefer the one which actually has a negative utility on cloud, so that also gets executed and tau 5 goes to the cloud. So in that case, we just pull tau 6 back to the edge, and then the execution continues. Yeah, so the next is like, how do we adapt to the variability? So before that, I would just explain some of the experiments that we did to motivate this kind of scenario. So over here, this is some of the benchmarks, the bandwidth measurements that we did using iPerf from a server that was connected in our like in our college network, and we were sending a request to the cloud. So we got this as the distribution, and we had around between 30 to 40 Mbps. But when we actually ran a simulator, which was using Sumo, which is like for urban mobility, and we simulated like around 7 edge devices across different parts of the city, which were connecting to cellular network like 4G or 3G. So using that, when we measured the bandwidth, it came like around, I would say, 2 to 4 Mbps, but not more than that. So such kind of variabilities exist. And because of this, we need to have some kind of adaptation strategy. And other thing also that we noticed, so it was that now that we are using serverless cloud and that scales well, that and all is fine. But earlier when we were doing our benchmark, so we used Amazon Elastic Inferencer that uses a GPU. So what happened there is that since it is a single point of contact, all the requests were getting lined up over there, and that was causing some delays in our inferencing request. So what we did was we monitored the tasks that are coming back from the cloud, and we had this average of the sliding window, and we calculated the observed cloud execution time, and that we compared with what we were expecting. So if at all there is a difference which is greater than some kind of threshold, we had to set the expected execution time as to what we are observing right now, and use that while we schedule instead of just using the actual numbers. So this we were doing, but one issue over here is that if at all we do that, and let's say the network time just increased a lot, then in that case, the expected execution time is going to increase. In that case, some kind of models for which these numbers have increased, they will never go to the cloud. So in order to remove such no points of returns, we had a cooling period, which means that after some point in time, you would just trigger another request just to check if the network has been stable or not. And then we continue doing that. So the experimental setup for this evaluation is that we had some real video feeds collected on the campus using the telodrones. And we used a Violet IoT emulation environment. So that lets us use Docker containers that emulate our edge devices, and they also emulate the drones. So for edge device, we did the core mark benchmarking, and we set the CPUs to 4 CPUs and 4 GB RAM, which is like the actual, it's a nano as well. And we had the drones as well, which are connected to the edges using Wi-Fi. And they had very minimal CPU because they don't actually do any computation, but they had some 100 MB of RAM because they are going to transfer the video frames to the edge devices. And our host server had these, since it was having only 32 cores, so we used the 7 edges and 7 to 28 drone containers, which means that every edge was supporting between 1 to 4 drones for each experiment. So for the FAS, we used AWS data center, and we used Mumbai as our location. And we used 6 possible workloads, which were generating between 8 to 24 tasks per second per edge. So this is like the overall workload description. Yeah, and we also used these 6 DNN models that we had benchmarked on the devices. So over here, you would see these. This is the expected execution time on the edge, which is in millisecond. And this is the cloud execution time in millisecond as well. So for getting the execution time, we benchmarked like over 300 frames to get like a distribution of the inference time, and we picked like 95th percentile for the cloud and 99th percentile for the edge, just to ensure that at least that much task gets executed within their deadline. And benefits was assigned based on how important any DNN model is for a particular application. And these edge cost and cloud cost are normalized based on the actual monetary cost that we pay. And then the utility is calculated using benefit minus the cost. And then we had 2 kinds of workload. One is the passive workload and the active workload. So for the passive, we just had 4 models activated. And for the active workload, we had all the 6 models activated. So one thing to note here is that these 2 models, oops, I think the box went above, but the body pose model, which is having minus 24 on as the utility, and hand pose model, these both were negative utility on the cloud, and they were not sent to the cloud. So some of the results, yeah, like, should I like pause for questions before going to the results part?
Up to you. So people online should either put the questions in the chat or unmute and ask them out loud. Any questions from the audience at this point?
So I had a question. So when you're in your earlier slides, when you said you were migrating your task from the edge queue to the cloud queue, right? Do you detect a global optimum scenario where like there could be a case where like the edge queue will just get starved, right? Because you'll keep pushing things to the cloud queue.
Yes. So that thing is mitigated by the work stealing heuristic.
Okay.
Yeah. So whenever the edge queue has a lot of slack, which means that it can support more and more tasks, so we always like pull tasks from the cloud queue. So at any point in time, we want the edge to be active.
Okay.
My question, what are the current limitations of the system? Because there are multiple layers of communication. So we have communication with drones and the base station and cloud. So what is the largest manageable system that could be served in that way? Can it scale like into 100 drones, for instance, or there will be required some modifications to it?
Okay, so one thing over here is that the number of drones that are being supported per edge, that would be limited by what the edge can support. And the other thing is, right now, we are showing results on the serverless cloud. So that supports, like that scales well with the number of requests. But if you actually use just one cloud server, that's where the limitation would be when the inferencing request will keep queuing up. So those are the two bottlenecks I can see in this system. Any questions on the Zoom?
I didn't see any. There are a number of participants, but we have no questions
Okay,
as right now.
all right. So I would move to the results part. So to evaluate our DEMS algorithm with on these workloads, we also designed some of the baseline scheduling algorithms like shortest job first, which achieves a very high task throughput, but it gets like a reduced utility and possibly also deadline misses. And then we have the highest utility first, which is supposed to achieve a higher net utility, but it might get us fewer task completion. Similarly, HPF, which is highest utility per execution time. This is also like a greedy variant similar to HUF. And then we have EDF, which is deadline aware and it maximizes on-time task completion. So these four, the first four are the variants that we tried for the edge scheduler only, which just uses the edge. And then we had one baseline where the heuristic just sends everything to the cloud. And then finally, we had one very minimal variant of edge plus cloud, where edge is just EDF and cloud is just FIFO without any migration or stealing or adaptation logic. So here are the results. So we have 5 different workloads, which is 2 drone passive, which generates 2,400 tasks, 2 drone active, and similarly, we did like a stress test of 4 drones, which are supported by each edge and for the active workload. So on the left-hand side, you would see this scatter plot that kind of shows the balance between the number of tasks successful on the y-axis and the total utility that has been accrued on the x-axis. So 2 interesting things. One is that for the cloud, if we would see, the number of tasks is actually very high because obviously that is infinite resource. And there is only a limitation if the task was not able to go to the cloud because of the negative utility. And but apart from that, the task completion is actually high for the cloud, but it suffers with a loss in the utility, which means that the utility of the workload, which is the 4DA, that is lesser than even, like the least workload in the case of edge-only scenario. So all the edge-only scenarios were performing like similar, but we had some analysis here and there. The other thing is that if we look at the DEMS, which are in these dotted circles, we have this trend that as and when we keep increasing the workload, the balance is achieved. So if we look at 4DA, the balance between this number of tasks successful and the total utility accrued is like the best balance over there. And that is, on the right, it is the same thing, but shown in a different format. Over here, we just show this as like, which is executed on the edge. And for the same bar, if we would look, the lighter versions show what is being executed on the cloud. So again, as we see over here, as the workloads keep increasing, the task processed by the algorithm increases, and the utility accrued is also like having the best balance over there. So yeah, so we conclude from these is that DEMS achieves the best balance between these 2 competing objectives. And when we look at the network variability, so we did one experiment where we were trying to change the latency between the edge and the cloud, like we introduced an artificial latency. So when we introduced this latency, it was more like a trapezoidal waveform. And once the latency is like on the peak, which is around, I think it was around 30 to 40 millisecond. So the cloud fail tasks started increasing, which is shown in the red. But when we were actually using the adaptation logic, which is DEMS A, if we look at this blue line over here on the top, that is constant because the observed execution, which is expected execution time, was constant in the DEMS. But in the case of DEMS A, the expected execution time was adapting to what was being observed. So because of that, the cloud misses reduced and the utility increased. So that's what we show over here. Like the task completion almost remains the same because we are not actually doing anything there. But the utility accrued increases because the cost is actually reducing. And similarly for the bandwidth variability, we did this experiment with the Sumo that we had shared earlier, right? So when we reduce the bandwidth, the tasks which are failing on the cloud, that increases a lot. But when the expected execution time that actually follows what is being observed, the utility increases. And finally, we have the weak scaling of the platform. So over here, we actually show the weak scaling of the platform, but more on the cloud side as well. So what we do is we have one host machine, which is supporting 7 edges, and number of drones is 2 per edge. So we have a total of 14 drones connected to a host machine, and that connects to our AWS. So when we keep on increasing the number of such instances of host machines, which means that we support around 56 drones in total, then the performance is actually similar. And in a recent paper, we have tried this for more than 80 drones as well, and the result still remains the same. So this is one of the hardware validation that we did. So over here, this is the Tello drone, and this is connected to a Jetson Nano, which is kept like nearby, and that is connected using a Wi-Fi connection. So over here, we demonstrate 3 different features. One is that the drone can follow a person who is wearing this kind of a marker, which is a hazard vest. So a model is running on the edge device, which is detecting the hazard vest, and it is trying to control the drone using a PD control, which is proportional and derivative control. And we observe that it also goes properly in these staircase or like different elevations as well. So the height, the front back, and the yaw motions are controlled properly over here. The other thing that we had demonstrated was in such kind of scenarios where the person falls, let's say, then we need to know what is their state and if they are in an upright position or in a kneel down position or like a fallen state. So we need to trigger some kind of command to the base station or like to emergency responders, and they can do something about it. So for this, we used the media pipe body pose and we used SVM classifier. So over here, you would see that it is showing that the fall has been detected. And yeah, similarly, so, and the drone also goes down when the person has fallen, just to stream the live video to the emergency responder. And the third thing is, for such an application where the drone sees, like drone can capture the videos, but how does the person communicate back to the drone? So they show certain gestures, and over here, when the gesture was shown, the drone is hovering right now and it's not tracking the person anymore. And yeah, after a point, so the gesture is shown again and the drone starts following the person. Yeah. And the last one is if you show something like 90 degree, it will land the drone. So this was the video. And if we put it all together, we have proposed a deadline aware scheduling across these multiple edge accelerators in the cloud. We have DEMS A, which maximizes our utility as well as task completion. And we have done an scalable experiment for emulated setup of 28 edge accelerators and AWS Lambda as the serverless FAS. And the adaptation greatly reduces the deadline misses on public cloud over WAN, and it improves our utility. So some of the ongoing and future work we have is like we try to integrate the scheduler with post-processing. So we are actually including the post-processing scripts now within the scheduler, and we are kind of guaranteeing some kind of QoS that these many tasks will be completed within these many seconds. So that's under review at FGCS. And after that, we also worked on some kind of algorithms where it was mobile edge plus a mobile fog along with the cloud. So we try to explore that as well, that as to how that helps. The mobility of fog also is coming into picture. So that's at PERCOM. So yeah, these are some of the publications, and acknowledgement to my collaborators and my lab members. Yeah.
Thank you. Questions from the audience or online? If you're online, you can put them in the chat or unmute yourself and ask it. So one thing, Suman, maybe you could comment on is what you're doing at ISI.
Oh,
So
yes.
people might want to know. Also,
Correct.
yeah.
So what I'm doing at ISI is I'm trying to come up with some kind of scheduling algorithms which is used for wildfire applications. So we are looking at these systems where drones can have, like drones are used for surveillance of any area which is under the wildfire. And they do 2 to 3 things. The first one is try and detect if somebody actually is needing help. So for the firefighters who actually show some kind of gestures, the drones can detect that they need help, and they can trigger a request to the other kind of drones like coordinator drones or so. And once that happens, we have to generate the path for these firefighters to some kind of a safe location. And since this is going to be like a wide spatial region, right? One drone cannot do everything. So we have this in a distributed kind of setting where there are multiple drones checking for people all around. And there are drones which fly at a higher altitude, and they are more like a coordinator drones. So they help generate the route for these firefighters and for even the survivors. And the other thing is, how do they do it in a very collaborative way? So one of the drones can take care of some spatial region, but eventually they have to work in a collaborative way. And the other thing is, even though the routes are generated or everything is going well, but since this is like emergency kind of scenarios, the wildfires keep spreading. So in that case, the coordinator drones keep monitoring if the fire is spreading in some kind of area. Then in that case, the escape route that has been generated for the people, that gets revisited. And the trajectory of the drones that is actually doing the surveillance, that also needs to be revisited. So this is like the gist of the problem statement I'm working here.
Thank you. Any other questions?
I was just curious. So, people like to say cloud is an infinite resource, but
Yeah.
in your experience, have you run into any limits? It could be specific to AWS India region, like
Yeah.
limits in terms of FAS or Lambda functions, like how many can be invoked? Like,
One thing. So I faced limitations. We started actually with elastic inferencing, and there we faced the request that it was not able to scale well with the number of requests. For the serverless, there is this thing that you can only assign the memory. We cannot assign any core count over there, and based on the memory, it allocates cores like within itself. So over there, you have to make sure that you assign significant amount of memory such that your task gets executed within time, because that like the cost is dependent on that memory. So you need to have that balance between how fast you want to get it done and how much you need to pay. So tuning that was a little tricky for me.
Great. All right. A final chance for the people online. All right. Well, thank you so much. Thank you, everybody, for participating in person and online.